This is the option topics again, and this is option C, Neurobiology and Behaviour, about which I know absolutely nothing, so good luck with this. I'm thinking I probably know more than you do. So, if a head injury has occurred, bleeding in the brain is possible. Okay, head scans can be performed to assess the amount of damage to the brain. We can have MRI or CT. So what do I know about those? You have to go into a donut, lying in a... okay. So they both give you kind of more or less the same thing, and one of them's good for bone and one of them's good for softer tissues. I think the MRI must be soft tissues, is what I'm thinking. And this one's good for sort of bones and tumours. This one takes about 30 minutes, and this one takes about 5 minutes. You see, I can read the booklet too. So, one advantage of using a CT scanner. State one advantage for a patient with a head injury. It produces an image faster. Nothing to do with electrodes. They're not screwing the electrodes into your head when they put those electrodes on. They're kind of gluing them to your scalp. It's not an invasive thing. I had quite a lot of people telling me, oh, you know, electrodes cause a lot of pain and trauma. Absolute nonsense. Anyway, there we go. Read your booklet. An MRI scan, so they decided not to use a CT scan after all, may detect excessive bleeding in the motor areas of the cerebral cortex in the right hemisphere of the brain. Suggests the effect. Okay. So, excessive bleeding. What do I know about excessive bleeding in the brain? Excessive bleeding in the brain may cause a stroke. I have to say I didn't bother reading the booklet for this because I know this off the telly. Resulting in paralysis. There are all those adverts. There's not just the staying alive one, there's the spotting the signs of a stroke one. If the right hemisphere is affected, the left side of the body will be paralysed. And we've got a pretty dodgy diagram of the brain. Now, I like to look at diagrams before I answer questions. So I know that bit's the cerebellum, and I know that that's involved with talking, walking, driving, typing. I know that that's the medulla oblongata. So that's heart and breathing rate. I know that that's the cerebral cortex. Or the cerebral hemisphere. And that's involved in sort of, you know, motor and sensory stuff. And then this bit in the middle, this is the hindbrain, midbrain, that must be the thalamus, which has got all those other little bits in it, like the hypothalamus and what have we. So, moving over here, I realised that Miss Knights, when she did this, has picked up the copy and paste, and that's C part 2. Because there's a C part 1, then it goes on to D on the next page. So I'm not going to answer that until I've answered this bit. Using the letters from the diagram. Letters, okay, so the letter goes in there. Name the part there. Use the letters from the diagram to complete the table to indicate the part of the brain involved in the following activities. Name that part. Okay. Regulating core body temperature. B. What's its name? Thalamus. Now I could have put hypothalamus because that's the bit of the thalamus that regulates core body temperature, and that would have been fine. Recognising faces, that's a thinking thing. So I'm thinking, haha, A. I amuse myself. Always thinking. I can't spell cerebral. Oh, there we go. There we are. And I'm going to put hemisphere, because I can spell it. Drinking from a glass. I'm thinking that is an automatic, I don't need to think about that. I can just pick a glass up. That'll be that stuff that you learn and then pass over to your cerebellum for control over. And regulating carbon dioxide concentration of the blood, breathing and heart rate, medulla oblongata. I have got to say, if you got that wrong, you want shooting. That is absolutely basic. If you're studying neurobiology and behaviour, you should be able to label and say what the functions of the part of the brain are. Heart rate increases during exercise. I wouldn't know about that. Describe how chemoreceptors monitor the change in rate of respiration. So, what do I know about respiration? It produces carbon dioxide. So if I've got increased respiration, produces increased carbon dioxide, and I know that's the thing that monitors, that regulates heart rate and breathing rate. And chemoreceptors detect the fall in pH as CO2 is acidic. And then we're on to part 2. Describe the role of the Cardiovascular Center. So how does it actually do to increase the heart rate? So the Cardiovascular Center in the hypothalamus, in the medulla oblongata, what does it actually do? That's what they're asking. So, if stimulated by chemoreceptors, so it's following on from that chemoreceptors question. The Cardiovascular Center sends impulses along sympathetic nerve and noradrenaline is released at the SAN. The SAN sends out more frequent waves of excitation. The more frequent the impulses, the more frequent the waves of excitation. Excellent. Oh, so turning over, and we've got a little change of direction again now on part D. So we're setting up an experiment to investigate the hypothesis that woodlice turn more in dry conditions than in moist conditions. Moist, what a great word. Woodlice are crustaceans that have gills that they use for gas exchange. What do I know about gills? I'm thinking aquatic, but here we're looking really at moist. Students set up 2 Petri dishes. One had moist filter paper in the bottom, the other had no filter paper. That doesn't look good to me. I'm thinking it should have had some filter paper in, just in case it was the woodlice responding to the filter paper. The student then observed the movements of the woodlice and counted the number of turns in a 3-minute period. And we've got the data. Number of turns, moist, dry, we've got mean, we've got standard deviation, and we've got the number of turns and how many times have they done it. 1, 2, 3, 4 by 1, 2, 3, 4, 5. So they've done it 20 times, and they've done that one 20 times. 1, 2, 3, 4, 5. 1, 2, 3, 4, 4, 5 is 20. Okay. Calculate a T-value, great, for the data using the formula below. Super duper. So I need to substitute in. So difference in mean values. So T equals, this is the difference in mean values, 15.8 take away 6.5, because that bar means that I need a positive number. So I'm going to, doesn't really matter, but it makes more sense to take the little number off the big number. Then we've got square root. S1 and S2 are the squares of the standard deviation of the sample. So I've got 2.61 squared over N1. N1 are the sample sizes, that's 20. Am I adding them? I'm adding them. 2.05 squared over 20, and I'm square rooting then the whole kit and caboodle. Now all I've got is a pretty rubbish calculator. So 15.8, I'm going to have to do it in stages. Take away 6.5 equals, so I've got 9.3 on the top. Then I've got over the square root, 2.61 times 2.61 equals 6.81, and I'm dividing that by 20. The square root of, so that's 0.34, and I've got 2.05 times 2.05 shared by 20, 0.021, so I'm going to do 9.3. I'm going to add together 0.034 plus 0.2, oh no, not 0.034, 0.34 plus 0.21, that's 0.55, square root it, so over 0.74, 9.3 shared by 0.74, 12.5, and it says 6/7, so I'll round it to 5.7. No point in going further than a decimal place. Any values? No, it's just a number. Okay, super duper. So, null hypothesis. So that means that there's no significant difference. And the critical values at 38 degrees of freedom, because we've got a sample size of 40 altogether, are shown below. Right, probability value. Always looking up P equals 0.05. That's my critical value, 1.69. Remember, critical value is the biggest down to chance value. So my T-value is bigger, so T-value is bigger than 1.69, so can't be down to chance, there can't be a no significant difference. I reject the null hypothesis at p is 0.05. That means that there is a significant difference. They really are turning more in dry conditions. That's what it means. What type of behaviour is being exhibited by the woodlice? So taxi goes straight there. Kinesis is running about, turning more. Kinesis. So how do I know? Explain my answer. How do I know it's kinesis? The woodlice move away from the stimulus. And what conclusion can we draw about woodlice behaviour? So what does this little experiment tell us? So we've established that they really are turning more in the dry. So in dry conditions, the woodlice turn more frequently. Increasing the chance of reaching a moist area. Or you could have done it the other way round, and you could have said in moist conditions they turn less frequently so that they stay in moist conditions. And then why do they do that? In dry conditions, remember the gills from up here. The gills dry out. That's why they do that innate behaviour. So, explain 2 ways in which we could have improved this. So 3 minutes, not very long. So we could have used observed woodlice over a longer time period. Can't imagine how dull that would be, watching woodlice run about for more than 3 minutes. I thought 3 minutes was your upper limit. And secondly, we've got this idea that we've got one had moist filter paper and the other one had no filter paper, and it should have done really, otherwise it's not a controlled experiment. Use dry filter paper in the base of the dry condition Petri dish. Okay, super duper.